All right, we're going to start chapters 15 and 16. All right, chapters 15 and 16 deal with mixtures, and specifically, we're going to spend most of our time talking about solutions. Okay. Chapter 15 is specifically about water type of mixtures, right, where we're going to use water as our solvent. We're going to talk about the difference between solute and solvent. So water specifically, and then in chapter 16, we're just going to talk about solutions in general, right? And we're to that point of the year where we're going to continually sort of branch off into these little different side areas of stuff that we've actually talked about already this year. We've already talked about mixtures way back near the beginning of the year. We talked about the difference between heterogeneous mixtures and homogeneous mixtures, but we really didn't do much more than that then. And now we're to that point where we should all understand enough chemistry where we can go into a little bit more detail and talk about these. And the reason that we have to do that now is because then when we get into the topics in the further chapters, after chapter 16, we're going to still be talking about this idea of solutions. And so it's a good idea that we get these details in now. So like I said, in chapter 15, we're specifically talking about water type of mixtures. And so let's just review a little bit about water, things that we know and have learned throughout the year about water. First of all, we know that water molecules are polar, right? And so they attract each other because they have a little bit of a positive end, that would be the hydrogen end, and they have a little bit of a negative end, that would be the oxygen end. The intermolecular forces that attract them together are called hydrogen bonds, right? Remember, those are the stronger of the intermolecular forces that exist out there. And since they have these relatively strong attractions for each other, these water molecules attract together, they have water then has these unique properties, like water has a high surface tension, right? All the water molecules like to hold together, and therefore the surface of water has a tension to it. You've probably noticed this before if you've ever jumped into a pool. If you jump into a pool, when you land on that water, depending on how you land, you can really feel that. And even though it's just water and it's a liquid and it's usually fairly easy to get through, there is a tension to the surface of that water. And it's not easy to get through, especially if you try to, cannonball your way in, or if you try to belly flop your way into the water. We also know that water has a low vapor pressure. This is one of those things that the groups in their presentations taught you about. They taught you about vapor pressure. When something evaporates, when a liquid evaporates, it produces a vapor pressure. But since water is attracted to itself, it doesn't evaporate very easily. And since it doesn't evaporate very easily, it has a low vapor pressure. And since it has a low vapor pressure, that also means it must have a high boiling point. One of the other things that we learned back from chapters 13 and 14 is we learned that boiling point is related to pressure, right? When something boils, when a liquid boils, that means that its vapor pressure has to equal the atmospheric pressure above it. When those two are equal to each other, then you have boiling that occurs. And since water already has a pretty low vapor pressure, then to get its vapor pressure up high enough to actually boil, you really have to get the temperature pretty high to get that vapor pressure up. Okay? So water has a relatively high boiling point compared to other liquids out there. One thing that we need to remember is that water is pretty unique, right? Not all liquids are like this. So here's a picture of water molecules. This is something that we've seen before this year, right? Water molecules are these bent molecules. Remember, we talked about different shapes of molecules. There's an oxygen that's single bonded to one hydrogen and then single bonded to the other hydrogen. The oxygen's more electronegative. It pulls on these electrons and causes the oxygen here to be partially negative and the hydrogens to be partially positive. That makes the water molecules then attract to each other, and the attractions are called hydrogen bonds. And so this is what liquid water would look like. You have all these little water molecules, and there's these little dotted lines that represent these little attractions that hold the water molecules together. So liquid water is fairly not organized, right? It's relatively random in how all the water molecules line up. But solid water, ice, right? Ice has a pattern to it. It lines up. So we're going to look at the difference between what liquid water looks like and what solid water looks like. Okay? And you notice the liquid water, all the water molecules are still attracted to each other, but they're not in a pattern. In fact, since they're not in a hexagon pattern, notice how they're closer to each other than solid water is. Now this is weird, okay? This is really strange. Why is this important? Because look at all this empty space. Look at all this empty space in the middle of these. That means if you have a lot of empty space in something, it's not very dense. So it turns out that solid water, ice, is less dense than liquid water. And things that are less dense always float. So this is why when you put an ice cube in water, the ice cube floats to the top, it doesn't sink to the bottom. That's weird. We think that's normal. That's not normal. Think about anything else. Let's imagine that you have some iron. You have a big chunk of iron. You can imagine if you had a big chunk of iron in your hand right now, it'd be really heavy, right? If you had a big chunk of solid iron in your hand. Now, I want you to also imagine that nearby we have this big vat of liquid iron. It's molten. It's been heated up till it's melted. And so we have this molten iron. And we're going to take this chunk of solid iron and we're going to throw it into there. Well, right now in your head's going, oh yeah, it's going to sink to the bottom. Of course it's going to before it melts eventually, right? But it's going to sink to the bottom because solids should be heavier than liquids. They should sink. Water's not like that. Water floats on top of the liquid when it's a solid. That's weird. Okay? So these are some unique things about water we need to keep in mind because we're going to start making mixtures with the water. Okay? All right. Oh, here's just another way of looking at the density of water. Notice how the density of water is listed there at different temperatures. So if you have liquid water, so that would be anywhere from 0 up to 100, right? Liquid water. Notice that it's most dense at about 4 degrees Celsius, so just above freezing. So it's still liquid, but it's really cold water. So cold water is most dense as it's going to be 1 gram per cubic centimeter. But notice what happens when it turns into ice. Notice the density drops quite a bit. This is why ice floats in water. Okay. Now, what happens when we mix things into water? Well, it depends on what we are mixing. Right? One of the kinds of mixtures that we could produce is a homogeneous mixture. This is something we talked about way back at the beginning of this year, right? Talked about different kind of mixtures. There's homogeneous, there's heterogeneous. A homogeneous mixture is called a solution, right? And how do you know when you have a solution? If one substance dissolves in the other, then it's always a homogeneous mixture, which is also known as a solution. So if there is dissolving happening, so for instance, if you put salt in water, you and I both know that salt always dissolves in water. Therefore, salt water is a solution. But if I were to tell you to put some sand in water, you've probably seen this before. If you put sand in water, I don't care how much you stir it, sand will never dissolve in water. Therefore, sand in water is a heterogeneous mixture. It is not a solution. Now, every solution, so we're just talking about solutions here. We'll talk about heterogeneous mixtures in a minute. Every solution has two parts to it. It has the part that's being dissolved, that's called the solute, and it has the part that's doing the dissolving, that's called the solvent. So solutes dissolve in solvents. The solute is usually the solid. The solvent is usually water. Now, it does not have to be. Solutions can be made out of any two things, really, as long as they dissolve in each other. They don't have to be solids and water. They don't have to be liquids or any. They could be gases and gases. They could be a gas and a solid. They could be lots of different things. But the ones that we're going to talk about the most often in here are going to be solutes, which are solids, in solvents, which are usually liquid water. The process of a solute dissolving in a solvent is called solvation. Right? And how do you know if a solute will dissolve in a solvent? We use the term like dissolves like. Right? What does that mean? That means that the solute and the solvent have to be attracted to each other in some way. If they're not, they won't mix. So if the solvent is water, and we know that water is polar, we just talked about that. If water is polar, then the solute would also have to be attracted to it. So it would also have to be polar in some way. So if the solute is polar and the solvent is polar, they'll dissolve in each other. That way we say it's like dissolves like. That also means that if I wanted to dissolve something in a solvent that was nonpolar, then the solute would also have to be nonpolar, because nonpolar dissolves in nonpolar. Polar dissolves in polar. Like dissolves like. Let me give you a little bit of an indication of what this would look like if we could watch something dissolve. So I have this little video here that's going to play.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
Right. You notice when you watch that video, right, that there was an attraction. The water had positive and negative ends, right? It has partially positive, partially negative end. And the salt has positive and negative ions. So the water can be attracted to the positive ions, and the other end of water could be attracted to the negative ions. And the positive and negative ions slowly get pulled apart and mixed into the water really finely. That's what we call dissolving. That's what we call solvation. Okay? All right. So some other terms that come up when we talk about solutions, and these are probably terms you've heard of before, right? You have electrolytes and non-electrolytes. If you have a solute that's dissolved in an aqueous solution that is made up of ions, so it's ionic like salt, then it will conduct electricity. We saw this earlier this year, right? If you remember up in the front of class, I put that setup that had the light bulb on it, right? And I were to put salt in the water and I held it up to the light bulb and the light bulb went on. Do you remember that? Right? That's because we created an electrolyte solution. All right? An electrolyte solution means that the solute conducts electricity when it's dissolved in the water. If it were not ionic, if it did not have ions, even if it dissolved in the water, if it did not have ions in it, it did not conduct electricity. When I put sugar in the water, and I did that whole thing. If you remember, the light bulb didn't go on because sugar is not ionic. It doesn't split into ions. Therefore, it's a non-electrolyte. Now, you've heard of the term electrolyte before you ever got to chemistry class. Can you think of where you've heard it before? Probably you've heard it before when you talk about things like Gatorade or Powerade, right? When you think about sports drinks like that. The commercials for Gatorade and Powerade always talk about how you're losing electrolytes when you work out. You need to get them replaced, right? So you need to drink more electrolytes. What does electrolytes have to do with you? What do you have to do with electricity? You don't get plugged into the wall and have to recharge yourself like your phone. So what do you have to do with electricity? Well, think about it. You have electricity inside you right now. Your brain produces electrical signals that travel through your nerves and eventually get to your muscles. The only reason you can move your muscles at all of your muscles, is because your brain is sending little electrical signals that stimulate your muscles to move. It stimulates your heart to beat. It stimulates your diaphragm to move up and down so you can breathe. It stimulates your arms and your leg muscles to actually move when you want them to move so you can walk around and hold things and write notes on your paper. All of that happens because electricity is traveling through your body. Now, how can it travel through your body? Your nerves would either have to be made out of metal, which they're not because you're not a robot, or they would have to be salty solutions, electrolyte solutions, right? And you actually know you have an electrolyte solution inside of you because you've probably tasted it before. Anytime that fluid comes out of you, it always tastes salty. And I'm not talking about urine, so don't get your mind there. I'm talking about things like sweat. And I know it sounds gross, but I'm sure you've tasted at some point in your life sweat. Right? Sweat is salty solutions coming out of your pores. That comes from inside of your body. Why do you have salt water inside your body? Because your body needs to conduct electricity. Every time that you cry, those tears are salty. Again, why? Because all of the solution inside of you is salty. You have salt water inside of you. You need it because you need it to conduct electricity. If you work out a lot and you sweat a lot, you're suddenly losing all of that electrolyte solution out of your body, and now your brain can't talk to your muscles very well. Well, that's a problem. If you're an athlete and you're playing a game, and you suddenly can't use your muscles very well in the middle of the game because you've been sweating so much, well, you're not going to do very well, right? You're going to cramp up. Your muscles aren't going to work very well. You're not going to be able to do the things that you want to be able to do. So researchers found years ago, they actually did this years ago, University of Florida, Gators. That's why they call it Gatorade, by the way. They developed a solution that has salt in it. So Gatorade is a salty solution that you can drink, except nobody likes drinking salty water because it doesn't taste very good. So what else did they put in there? Sugar. What does the sugar do for you? Really nothing, except just make it taste better. Plus they could put some flavoring in there and whatnot. So electrolyte solutions like Gatorade and Powerade are there to help you replenish all of that salty water that you sweated out when you were working out. So what happens when you drink Gatorade and Powerade when you're not working out? That's a problem. You don't need all of that salt water. So if you're just sitting on the couch and you're not doing anything and you're drinking Gatorade or you're drinking Powerade, stop. I know the Gatorade and Powerade people won't tell you that because they want you to buy their stuff, but you don't need it. All right, you only need it when you're actually losing all of your electrolyte solutions. So here's some visuals on that. Okay, here's another one of those light bulb setups, kind of like what I had, except it's not on a big ring stand. You see in photo A there, we've got ions that are actually in the solution. You can see the little positives and the little negatives, they're in the solution. And if the little positives and little negatives are floating around in the solution, that means there are free ions, so that's an electrolyte solution. The light bulb goes on. Notice in the next picture, in picture B there, that there's ions. There are some positives and negatives, but not very many. Since there are fewer, then less electricity can go through that solution. So that's a weaker electrolyte. Okay, so the light bulb doesn't go on as much. And then finally in C, you have something like sugar in that picture that has no ions, no positives and negatives. Therefore, it's not going to conduct electricity at all. It's a non-electrolyte. So in picture A, we had a strong electrolyte because almost all of the solute turned into separate ions. In picture B, however, we had a weak electrolyte. We still had some ions, but not very many. Okay, so electrolytes can be strong or weak, or you can have a solution that's a non-electrolyte. Those are some terms you're going to need to know about, okay? We also have something that we talked about a few chapters ago called hydrates. Remember, hydrates are ionic solids where water is trapped inside of them instead of the other way around. Instead of having salt dissolved in water, we could have water dissolved in salt. It's called a hydrate. Remember how we write them? You see in the chart here where you have the formulas with the little dot in them. Remember, that dot is not multiply. That means attached to. So we have MgSO4 with 7 waters attached to or trapped inside the MgSO4 crystal. So magnesium sulfate heptahydrate is what we would call that. And a lot of these hydrates have common uses. As you can see, some of them have common names that we use for different things. Okay. If you have an ionic solid that doesn't have any water in it at all, we call it anhydrous. And I think we've talked about this before, where if you look at an ionic solid, like in this picture here, you can see this is copper sulfate, CuSO4. Copper sulfate is blue when it has water trapped inside of it. But in the anhydrous version, if we cause the water to evaporate out of it, notice it turns white. All right, so you can tell the difference between those. All right, finally, we're going to put all this together. We're going to look at all the different kinds of mixtures that are possible. So I want to bring back in this idea that there's also heterogeneous mixtures out there too. Not everything's not just a solution. Not everything dissolves. So let's talk about the different kinds of mixtures that are possible out there. Suspensions, colloids, and solutions. Now, a suspension is a heterogeneous mixture. So is a colloid. But as a solution, we just talked about, is a homogeneous mixture. So now, how do you tell the difference between these? Okay. Well, a suspension, when you look at it, has the particles either float or sink, but they never stay mixed. So, for instance, if you put sand in water, right, and you mixed it and mixed it and mixed it and mixed it, guess what? Nothing is going to change about it. When you stop mixing, all the sand is going to sink to the bottom of the water. It never stays mixed. That's called a suspension. A colloid, though, is where you might have particles that mix really well, but they don't dissolve. So they stay mixed, but they don't dissolve. So for instance, if you were to have something like toothpaste. Toothpaste is made up of a whole bunch of things that's dissolved in a little bit of water, and it makes a paste. That paste, that stuff that's mixed in there is not dissolved, but it stays mixed, right? You don't have to like shake up your toothpaste and mix it to keep it mixed. It stays mixed all the time, but it's not dissolved. Solutions, however, are particles that mix so well that they actually dissolve. Now, when you're looking at these three, the suspension is the easiest one to tell by eye. Why? Because you can actually still see all of the particles floating or sinking in there. But colloids and solutions are hard to tell the difference between because they're both mixed really well. So how do you tell when something's dissolved and when it's not dissolved? If you shine light through through a suspension and a colloid and a solution, something weird happens. It's called the Tyndall effect. The light, when it hits little particles that are floating around in the water, will scatter. So if you shine light through a mixture of sand and water, obviously you can see where the sand is, right? The light will hit it. In a colloid, the same thing's going to happen. The light's not going to go straight through there. It's going to bounce off the little particles. You'll be able to tell in a colloid. But a solution, no Tyndall effect. If you shine light through, let's say, salt in water, the salt is broken up into such small particles that light can't even bounce off of it. And the light goes straight through just as if it were pure water. Okay? Last thing about all three of these, suspensions, if you were to put something in the water that is a suspension that doesn't mix, it does not affect the properties of the solvent. That means the water will still boil at 100 degrees Celsius. It'll still freeze at 0 degrees Celsius. That doesn't change. Same thing with a colloid. Colloid doesn't dissolve in the water, therefore it doesn't affect the properties of the water. But if something dissolves in the water, it does affect the properties. So that means that the water is not going to be able to freeze at 0 degrees Celsius, not going to be able to boil at 100 degrees Celsius. Those are actually going to change. If you put salt in water, it no longer boils at the same temperature you thought it was going to boil at. If you put sugar in water, same thing. When it dissolves. But if you put sand in water, the water will do the same thing it normally does. So let's talk about some examples. Right? So I already talked about sand in water as an example for a suspension. Oil in water would be another one, right? Oil and water. So if I put oil and water, they don't mix at all. The oil always floats to the top, no matter how much I stir it. Cereal and milk would be another suspension, right? The cereal always either floats to the top or sinks to the bottom of the milk. It never dissolves in the milk. Okay, maybe some of the sugar on the outside of the cereal dissolves in the milk, but the actual cereal itself never dissolves in the milk, right? Now here's some colloids. This is the tricky one. Colloids are the ones that are not dissolved, but they are well mixed. Toothpaste I mentioned before. Smoke in the air. Smoke doesn't dissolve in air, but it certainly mixes really well into the air. Hairspray or Jell-O, right? So those are all examples of colloids. Solutions, and you probably know most of these, right? Be things like salt in water, or sugar and water, or alcohol and water. Air is a solution. That's the oxygen and the nitrogen and a few other gases that are in air. All of those are dissolved in each other, evenly mixed, homogeneous, evenly mixed. Brass is an even, homogeneous solution between copper and zinc. Okay. All right. So that's the chapter 15. Chapter 15 is relatively short. We went through it pretty quickly here. So go back through, make sure you understand those terms. It's a lot of vocab terms. That's what chapter 15 is all about. And then what we'll do is we'll get into chapter 16 on Wednesday, and it'll use some of these terms. So make sure you're going back and you're working on the homework problems that go along with chapter 15, so that when you get to Wednesday in chapter 16 and we start going through that, it makes a little bit more sense. All right?